3 with K's. We are going to take a look at lines and curves in space because we have them, right? I was taking this thing apart in my Calc 2 class because we did some. So, yeah, look at that. It's a three-dimensional curve in space. There is equation to this. It might not be pretty, but there is equation. And for this particular piece of wire, we can actually, because it's easy, we can straighten it up and then we can measure the length. But what are you going to do with the road that winds around the mountain, right? And you don't have Superman's phone number. So you can't straighten that one out. So you would have to compute the length of that road either by driving on that road or actually figuring out what is the actual function that, and then you can find the length of the curve and so on. So we are going to learn now how these curves are represented in space. We are going to learn about vector-valued functions. So now, instead of having a vector of numbers, the vector will contain functions in each one of the spots. So you will have, we'll call that vector R, and then we will have, let's say, f of x, g of x, and then, or f of t, g of t, and then, let's say, h of t for components. So we are going a step up in hierarchy, going from numbers, upgrading into functions. So let's see what we can get here. So the first thing is that if I have any kind of curve in space, and that lives in our 3D x, y, and z, I can trace along the line the position, and as you can see, there are infinitely many vectors which stretch from the origin towards the line, and each one of these vectors is going to be called, by all of them at the same time, are called vector R, and that vector R is in terms of functions. So f of t, g of t, and h of t. Oh, perfect. Book is using x of t, y of t, z of t. All right. Or, to make the book happy, x of t, y of t, and z of t. Perfect. You can use whatever letters you want. Now, this t is the good old parameter from your Calculus 2 course. And I really hope that all of you guys studied parameterization at the end of your Calc 2 course, because that is essential for success in this class. So t is going to be parameter. And you can think of this t as time, because as you can see, as time passes, you end up at different positions along this line. So vector R is called the vector, the vector-valued function. So that's your R of t. And just to give you a very simple example and a progression of how mathematics works, you first learn numbers, right? Like numbers 7 and negative 13 and so on. So you have numbers, then you upgrade it into variables, then you upgrade it into functions, and then you said you can plug in numbers and obtain other numbers, right? So if you have in your pre-calculus course that f of x is equal to x plus 5, then f of 2 is 2 plus 5, and it gives you 7, so you have the input and you have the output, right? So that's what we have. But then what you can do is you can do the same thing with vector-valued functions. So these are actually numbers at the end. They are functions for some time until you plug in the value and compute them. So you all understand the concept of the function and the concept that if you plug a number in the function, you get the output on the other end. You are hopefully all aware of that. So now we have the same principle upgraded for vectors. I have vector r of t, which could be, let's say, t squared e to the t and then sine t, just to put in some variety over there. And then I can compute this at various values. Let's compute how much is r at 0. R at 0 is going to be 0 squared e to the 0 sine 0. Because what I'm doing is I am replacing every t with 0, just like I replaced earlier every x with 2 in the example up there. So now what is the r of 0? R of 0 is 0, 1, 0. You see? You get the vector that has numbers on the other end. You can also compute r, let's say, pi over 2. So you will get pi over 2 squared, e to the pi over 2, and sine of pi over 2. That can be simplified. So r of pi over 2 is pi squared over 4, e to the pi squared, and then sine of pi over 2 is 1. Now you can go take your calculator, you can punch some numbers, don't punch, I mean, you know, push the numbers. And you will get decimals and you will know where to graph that vector. So in some sense, just like in your middle school when you do the dots and to find what the function looks like, you assign all the x's and you compute y's and you know have the dots and you connect the dots, right? You can do the same thing here. You can compute all of these points, all of the vectors, and you graph their terminal points because the initial one is always at 0, 0. You graph all of these points and you can connect them and you get the curve in space. So we just upgraded a little bit. Now, also what I want to mention is that, and I already said that t is the parameter. I'm just going to do this, and it's in red, so it's extremely important. These guys are parameterization. This is parameterization. Of the curve. It could be line as well, whatever. So parameterization. So we would like to learn, first, we would like to learn the easiest creature. And the easiest creature is the straight line. So we start with learning about the straight line. We have the notion of the slope and the y-intercept from the good old algebra. Y equals mx plus b, where m is the slope and b was the y-intercept. So you would start graphing at the y-intercept, and then you would count out the slope, rise, run, and you would set the line through those points. So this is what you did earlier. The two important pieces of information that you had to have at all times was b, which is the y-intercept, and m, which is the slope. And then you use that in pre-calculus, you use that in calculus for tangent line, over and over and over again. Now we are moving into 3D lines. And the 3D line is not only going to live as a straight line on the xy plane. If you guys have a straight line that is on the floor, well, you just have this, y equal mx plus b, because the floor, we agreed all last time and time before, right? The floor is our xy plane. So all of the functions that you learned, including that one, live on the floor, not above, not below, just in the plane of the floor, this wonderful carpet we have. So we can do more than that, because in 3D, here is a line that is not on the floor. It's right here. And my question is, what is the equation for this line? And let's pretend this extends indefinitely in both directions. What is the equation of this particular one? So it should have the same features. It should have a 3D slope, and it should have a point that is fixed in space, and that should be enough. Because if you have a one point that is fixed in space, and then there is something that tells you direction away from that point, then the line is unique line in that spot. So let's see how we can construct that in space. We have our three-dimensional x, y, z coordinate system. And we are going to pick a point somewhere, and that initial point is going to have coordinates x0, y0, z0. It can be anywhere, anywhere. Now what's going to happen is that from that point, I'm going to draw some vector v. And the line that we are looking for is going to live along that. L. I'm going to find another point x, y, z over here. And I'm going to stretch these construction vectors that we will try to understand. Now that you have this picture, let me write that your equation is going to be this initial point plus TV. And I claim this is the line in space. Should have done it in red, but I can put the red box around it and also underline that one. It's a vector equation. Yes.
Does that only work in 3D, or is it the same equation with two points with different dimensions?
All dimensions. This is any dimension. All right, now we have to understand. I haven't explained anything about this. I just wrote the equation down, and that's it. So let's think about this equation and see what it is actually. So what is this R? R is right here. R is the vector x, y, z. R0 is the vector x0, y0, z0. Plus t and then there is this still mysterious vector v. Now, I'm going to call this vector v. Sorry, I'm going to give it A, B, C components. And I'm going to say here, plays the role of slope. That vector, ABC, carries the direction of the line. And I hope you guys see that the blue vector V on the picture, blue vector V on the picture and the actual line L, which is the black line going through V, have the same direction. Now also from standpoint of addition of vectors, multiply this by t over here. Look what you have. I'm going to circle things and then I'm going to erase it. So hopefully you guys are going to watch at the projector. So, and the equation at the same time. R0 plus Vt. You see how they're head to tail? They're ready for the addition. Head to tail method to add vectors. So R0 plus Vt is equal to resultant is R. So that's why the vector equation over here is the way it is. R is equal to R0 plus TV. Now, I am showing you the representation of what R is, what R0 is, and what V is in terms of X, Y, Z, X0, Y0, Z0, and then ABC. That means that you can break this one into three equations. X equals X0 plus AT, Y equals Y0 plus BT, and Z equals Z0 plus CT. I'm going to box this, and then I'm going to box it again, and then I'm going to box it one more. Now I'm going to put in a cloud. You guys put stuff on the cloud now. There we go, cloud. This is parametric form. Parametric form of the line in space. Two equations are the same, except the one on top is compressed form and the one on the bottom is in exploded form. You don't have y equal mx plus b now. In calculus 3, most of the stuff, since we are dealing with a third-dimensional space, most of the stuff will be parametricized with three separate equations over the parameter t. So we are introducing the fourth unknown, which is parameter t, and we're going to do everything in terms of that t. So t is the thing that binds them all. You cannot write one single equation for all three. Now, you can actually write a three-sided inequality if you want to, because each one of these equations can be solved for t if you are careful. So x minus x0 over a is t, and y minus y0 over b is t, and z minus z0 over c is also t. And since you have all of these t's, then you can just equal all of these. Now, this is also one of the ways to represent the line, but why, right? So that's yet another way to represent the line. The one that you will be using is the one that we just uploaded on the cloud, right? That's the one that you will be using all the time. So now I'm going to ask you, since you are now experts on lines, I'm going to ask you to find the equation of the line. Now, when I say find the equation, that means those three equations, right? Equations. You have to have the parametric pair, or three of them. So find the equation of the line which goes through points. Your band is expired, so what are the points? Like -1, 3, and you are banned again. Cool down for a day, so we'll talk again Monday. Square root of 4 is 2. And I'm going to use it just because. And what's the second point? 2, 3, you just scrambled this one. Like, how little effort can we put into coming up with numbers? That's okay. I mean, we used even signs, so that's okay. All right, let me see how you're going to deal with this. Think about it. You have 2 points. What can you create when you have 2 points? Vector. Which vector do you get? V. Good. Pick one of the 2 points as your x0 thingy. R0 thingy. Because you will see that these 2 points over here, when you find the line has to go, because the line has to go to those 2 points, and the vector V is good period of the school. I mean, I understand that iPhone has no case because people are used to buying that. Not anymore. Certain qualities will never be lost. All right. Let's take a look at the solution of this problem. Many of you are doing very well. Michelle, you had the question?
No, never mind.
All right. So we are going to use this as, let's say, x0, y0, and z0, and this could be x1, y1, z1, 2 points in space. We know when we want to find the vector between 2 points, we subtract the coordinates. So our vector v is going to be given by 2 minus minus 1 is 3. 3 minus 3 is 0, and negative 1 minus 2 is negative 3. If you subtract it the other way around, it doesn't matter. You're still getting the same answer. So we have our vector v. We have our equations from the cloud, which is x equal x0 plus a t, y equal y0 plus bt, and z equals z0 plus ct. We have x, y, z stay where they are. Our x0, y0 is negative 1, 3, and 2. Plus, no, minus at the end. 3, and then 0, and then negative 3, and then t, and t. So what is the actual answer here? The actual answer is x equals negative 1 plus 3t, y equals to 3, and z equals to 2 minus 3t. If you want to write it as a parameterization in terms of vector valued function, you can also write it negative 1 plus 3t, comma 3, comma 2 minus 3t. I'm sorry? One of the 2 points that are given.
So I made the same one to my initial, but I got a negative 3 as a positive 3.
Yeah, which is just the vector is a different, right, orientation, but it's still the same line, because if you have all of the signs backwards, it is still the same, right? Actually, your question was about 2 parallel vectors. Remember that we only switched the sign, right? So there we go. Are we all at least semi-happy about this? At least, because you still have to do homework to become very happy with this. Good?
So that's the vector RT. That's
Is it Rowan approved?
That's the final form.
You're from Rutgers. I said, is it Rowan approved university? Yeah, okay, good. Penn State is back in his seat, I see. It's good. We're... Oh, yeah. Did not have to wrestle. All right. I'm sorry? So we have equation of the line. We are done with the equation of the line. The only other thing that we can talk about is the equation of the line segment. Now, line segment is, the line that it's finite. It's not infinitely long. Right, Matt? Exactly. So, line segments have the finite length, and the way to limit those lines to have the finite length is we limit t to go between 2 values, because t is the one that draws the infinity of the line. We are going to use these line segments later, so we need to understand how this stuff works. So if I have the solution presented in this way, and there is no limitation on t, that means that t goes from negative infinity to positive infinity, and this line will be stretching indefinitely in both directions. But then I can actually pose the limitation on it. So let's say given line r of t is equal to, now I'm just going to make this up so I don't have to disqualify anyone, plus minus 2 minus 5t, give you disqualified, 3t, and then negative 1 plus t. There we go. Find endpoints. Find endpoints of the line segment with t being trapped between 0 and 3, let's say. All I need to do is to plug in 0 and then plug in 3, and I will obtain 2 points. Those are the end points of the line segment. So when I do this, this is going to be our regular line, the whole thing. But then somewhere and somewhere are going to be the 2 points. This one is t0, this one is t is 3, and this portion here is the line segment. It always has the finite length of whatever it is. So now you can plug in r of 0 is going to be 2, 0, and -1, which means 2, 0, -1 as a point. And then r at 3 is, who chose these numbers? 3 minus 15 is -13. And then another 3 is 9. And then another 3 is 2. So we have -13, 9, and 2, which is another point. And if you want to know how long is the line segment, you can just run the distance formula, right? That's it. This is going to come up later in our calculations in chapter 14 and so on, and also chapter 13 is going to have something about it. So let's keep this in mind. We are done with straight lines. We want to see the curves in space. So that, right? What is the equation of that? Because if this was made out of something that cannot be straightened out, I still need to be able to find its length by calculating some numbers somehow. So now we are supposed to learn how to deal with this. Well, I'm going to draw the same picture as before. X, Y, and Z. I'm going to have some curve there. And we are going to, again, look at the vector r. And we're going to remember that vector r of t was the vector valued function f of t, g of t, and age of t. Also, we can use the ijk notation. We don't, but you can use hats because they're unit vectors. And we are also going to take a look at the, since you are introducing the parameter t, you have another degree of freedom which gives you the direction of the motion, which is the orientation. So that concept, you see, if this was t equals 0, t equals 1, t equals 2, t equals 3, you see that the motion goes that way. Do we all agree on that? So direction of motion is the orientation. Direction of motion, I'm just going to put t equals 0, then t equals 1, then t equals 2, ... is the orientation. Again, it will play a role later on. We're just defining it now. So the three equations, three functions within the vector valued function describe this curve 100% in space, and then we have the direction of motion as the fourth component in addition to those three, because technically we have four variables, right? We have the t, we have x, we have y, we have z, which is each point in space, and then we also have t in addition to everything, and that t is what grants us another degree of freedom, which is going to be reflected in this orientation thing. So what is the first thing that we want to study? Well, obviously helix, right? Because DNA. Why not? So what is a helix? Anyone? I'm sorry? That's DNA. What's the helix? It's a spiral. That's what helix is. And this is the side view. If you look at the top view, all you see is a circle. Top view. Helix on the side view. You're going to have your, let's say, coordinate system go like this, x, y, z. Now helix can wrap around any axis or in between, doesn't matter. Z is shooting straight at you as you are looking at the paper for the top view. Right now, what is the equation for the helix? Well, we see it's circular in its x and a y direction. And we know from calculus 2, parameterization for circle, otherwise death. So R of t must start as R cosine t, R sine t, because that is going to parametricize the circle. And then depending on how the last component looks like, we are going to have different types of a rise for a helix. So if it's t, it's going to be linear rise, which means that each one of these will be equally spaced as it goes up. So this distance here is the same as this distance, the same as this distance. If it's a t. But if you put t squared, you can put e to the t, you can put ln t, you can put any other function there, then it's going to have a larger rise or a slower rise. Now, at this point, I mean, it's good to take apart a pen. If you have one of those pens that you can click, and I don't, that you can change the ink, and you take that spiral out, what you see what spiral does, it goes around, and it clusters, right? So that could be, oh yeah, you have the spring? Perfect. Excellent. So as you can't see over here, because it's too small, there is the equal spacing, and then it collapses into. Now, how would you achieve something like that with the mathematical thinking? With the mathematical equation, if anyone would like to take a look at the spring, if you've never seen one, it's right there. You can do experiments with it. You can also play a mini basketball with it if you want. No. So you can achieve various things with this. You know how e to the x looks like this, and e to the negative x looks like that. So observe how rapidly it falls here, right? So your spring, your helix can do this. Like that. Because it takes a long time. So the x and y components, they don't change. They're always going to be whatever the radius is times cosine times sine, right? It is the z component, the third component. The function that sits there that will tell you whether these are equally spaced, right? Or symmetric, nice healing. Or if you have something like this, which will do this eventually. So that is the part when you do mathematical modeling as engineer that you have to figure out. What is the appropriate function to use to accommodate whatever your application is? All right. Now let's see. So that's helix. Roller coaster curve. Let's switch to the textbook and take a look at the roller coaster curve. I don't know any roller coasters that look like this, but here it is. And if you look at the top left corner of that picture, you see that the base is still circular, and since it's the length 1, it has 1 times cosine t and 1 times sine t, which is just, you don't have to write the 1. And then you have 0.4 sine 2t for the k, which actually creates the curve to do this. So x and y component give you a perfect circle, and it is the z component that bends it in this way. Now I hope that all of you guys can see the circle, and then you can also see a sine function wrapping on the edge of that. So look at that. Slinky curve. You know those what is called that thing? Well, it's called Slinky, right? You know the Slinky. Connect at the end, and you get the Slinky curve. You know the equation for it now. How cool are you, actually? Next time you encounter like a 5-year-old with that thing, sit them down and explain everything about vector valued functions and how to obtain this curve. Do what?
I'm trying to teach my 5-year-old cousin so
Yeah, next time you have to record that because the YouTube is hungry for things like that. And if you don't, I'll post it on my channel. It's okay. Like my student trying to learn, trying to teach the 5-year-old the shell method. So we have the Slinky. Now, thinking about these concepts, most of this, guys, is going to be you figuring out how these things look in space. And that is done through graphing many of these in space. Not on your calculator, because your calculator is completely useless here. You have to use Mathematica or some other advanced software and then graph this. And then it can be rotated in space and you can check it out and try to find all of these features. I would like to, one more time now, unfortunately I can't, they don't have zoom feature here, so I can't zoom in more than this. But if you are to look at this shape from the top, with something like this, some piece of wire that was bent in this way was sitting on the floor and you look at it from the top, you are going to see a perfect circle. And you have to see a perfect circle because, which will have radius 1 because of the 1 and the 1. These two are telling you that xy is a perfect circle. And it's this one that is going to draw the sine along the edge. You know how sine looks like. It starts in the middle, it goes up and then dips down and then goes up and then dips down and then goes up and then dips down, right? That's what sine curves do. Go up and down and up and down. That's why it's curved in this way. Look at on the top, perfect circle. Look at sideways. You can see if you are to rotate that wire, you would see a sine function doing this. Right? If you are to look sideways. So now what you do is you start playing with these things. What do I get if I have this? What do I get? And that's how you learn. It is not, yeah, I know helix, I'm good to go, because no, right? Maybe one day you want to construct those roller coasters, right? And then that's going to be this, figuring out, and then you will have to figure out some forces and some velocities and accelerations. So you have a launch pad, you have the roller coaster that actually gets to the point B eventually. All right. So we have lines and curves in space. So now what did we do? We discovered a way to represent lines and curves in space, which are actually now our 3D functions. And what else are we interested in? Once we have functions, we want to know about limits and continuity. Now, what is the limit? You learn in Kalk 1 the epsilon delta definition and all that kind of stuff. What is the limit in a nutshell? It's a fancy way to compute y values. That's what it is. That's what the limits are. It's not a maximum value. It's not a minimum value. You know that because you drive, right? It says speed limit. Your car doesn't explode when you exceed it, right? That's why you do it. So the limit is not a maximum or minimum value. The limit is simply the other way of computing the y values, or in this case z values, for a function. Now, if you have a point where function does not exist, your pre-calculus method, which is you plug the value in and you try to compute, falls apart because there is no value. You can't plug it in if the value is missing. But limit does work because limit doesn't compute at the point. Limit computes at all points around that point, but not at the point. So calculus can compute in that case. So now we want to extend these ideas to vector-valued functions. We know how to find, hopefully, we know how to find limits of functions. How do we find limits of vector-valued functions? Well, just component-wise. You find a separate limit for the first function, which is in the x spot, and then limit for the second one in the y spot, and the limit for the third one in the z spot. So technically, you will be doing 3 Calc 1 problems per each Calc 3 problem. And that is going to stay like that for the rest of the Calc 3 class. So limits and continuity for vector-valued functions. Yes. The screen. What did I want to say before you said the screen? Break time? Break times for the week. We just power through. Now is a good time to drink the 5-hour energy because we are actually stopping at 2 a.m. tonight. So this is the perfect time. Concerned? You go till 2, right? Because you do homework till that time anyway. Yeah. Let's take a look. So we have our vector valued function f of t, it's a terrible t, g of t, and h of t. To find the limit as t goes to some value a of this r of t, we will simply find individual limits for each one of these. So limit of f of t as t goes to a, comma, limit t goes to a of g of t, and limit h of t as t goes to a. Continuity is also done component-wise. If all of the participating functions, f of t, g of t, and h of t, are all continuous, the whole vector-valued function is continuous. If any one of those is discontinuous, then the discontinuity will permeate through, and the r of t would be globally discontinuous. So continuity is also done component-wise. I'll put word done under quotation marks. If any of the functions are discontinuous, then r of t is discontinuous. Now, to check continuity, you remember, hopefully you remember from, the ancient times, you did Kalk 1. There is the theorem that says that all polynomial functions are continuous, all exponential functions are continuous, all logarithmic functions are continuous on the entire domain, sines and cosines. And then you have the discontinuous one, like 1 over x for most of those. Tangent, cotangent, cosecant, and secant, they're all discontinuous somewhere. Square root functions are continuous, so radical functions are continuous. Inverse trig, well, some of them they're not functions though, but if you restrict the domain, they are continuous. So we have continuity that just permeates through this. Okay, and that's it. I hope you're not disappointed. All good? All right, so we're going to stop the screen and resume it at some point later when we come back with 11.6.